Friends, welcome to my channel. Dhanesh here. Today I am going to discuss about quantum entanglement. The theory behind quantum entanglement challenged the prevalent theories of physics and the beliefs of the most famous scientists. So I start off by sharing the quotes of Albert Einstein and Stephen Hawking, the most famous scientists of all time. Let's start. See, quantum entanglement. So first, let me discuss about Einstein's quote about the universe. This is the quote from Einstein. As I have said so many times, God doesn't play dice with the universe. This is the quote from Albert Einstein. This is the quote from Stephen Hawking. Not only does God play dice, but he sometimes throws them where they cannot be seen. So what is this quantum entanglement? Now I am going to discuss about the most weirdest phenomenon in science, quantum entanglement. After understanding quantum entanglement, you may think God may play dice with the universe. What is this uncanny phenomenon, quantum entanglement? See, quantum entanglement is a phenomenon observed at the quantum scale or atomic scale where entangled particles stay connected so that the actions performed on one of the particles affects the other, no matter the distance between two particles, even at a distance of light years. Next, I am going to discuss, we need to understand how we can create these entangled particles, how wave function and entangled particles are related. That's what I am going to discuss. So first, let me talk about wave function. See, wave function in quantum mechanics, a variable quantify or a variable quantity, a variable quantity that mathematically describes the wave characteristics of a particle. The value of the wave function of a particle at a given point of space and time is related to the likelihood of the particles being there at the time. It is possible to separate two subatomic particles and both are described by a single wave function. These two particles are entangled. See, how do you create quantum entanglement? That's what I am going to discuss now. For that, this is the experiment, a simple experiment. We can, by using this simple experiment, we can create quantum entanglement. The vast majority of quantum entanglement experiments to date use photons as the entangled particles, for the simple reason that it's really easy to entangle the two photons. In these experiments, they put a bunch of calcium atoms into a highly excited energy level where the electron is forbidden to return to the ground state by emitting a single photon. The emission of one photon is followed within a few nanoseconds by the emission of the second. These two photons are entangled. So this is the way you can create entangled particles. Now, how spin is related to quantum entanglement? That's what I am going to discuss. In quantum mechanics and particle physics, spin is an intrinsic form of angular momentum carried by elementary particles. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. By law of conservation of angular momentum, spin is conserved spin is constant. Consider a parent particle, it's shown in the figure, with 0 spin, and let it decay into two particles. As discussed, spin is a conserved quantity and it can never change. If the parent particle has zero spin, then the two daughter particles must have opposite spin. So if one has a spin pointing left, the other one must be right. If one is up, the other must be down. Hence, when we add the two, we get 0, and hence the spin is conserved. The angular momentum is conserved. This is the simplest example of a pair of entangled particles, and they are governed by a single wave function. Next up, I am going to discuss about Einstein's spooky action at a distance. See, as long as the entangled particles don't interact with anything, you can separate the particles feet, miles, or even huge distances, and the two particles are connected by a single wave function, and they will have separate spin. As you know, the quantum world is intrinsically probabilistic. We can't predict the outcome of a measurement before we make it. It's really uncanny when we measure the spin direction of the both entangled particles. If the horizontal spin direction of one particle is left, then the spin direction of the other particle must be right. We can measure the spin direction of the two particles in quick succession very fast. We know that the fastest thing in this universe is light. 1 foot in 1 billionth of a second, or you know the speed of light is 3 into 10 raised to 8 meters second raised to -1. Let us assume that the two entangled particles are separated at 1 foot. After measurement, we understood that the quantum information can travel faster than light. Albert Einstein dismissed quantum entanglement as spooky action at a distance. Over the past few decades, however, physicists have demonstrated the reality of spooky action over ever greater distance, even from Earth to a satellite in space. The minimum speed of the entanglement is 1,44,500 times the speed of light. Next is I am going to discuss about BOHR-EINSTEIN debates. This was really important at that time. The BOHR-EINSTEIN, even now as well, the BOHR-EINSTEIN debates were a series of public disputes about quantum mechanics between Albert Einstein and Niels Bohr. Their debates are remembered because of their importance to the philosophy of science. Bohr proposed that entities such as electrons had only probabilities if they weren't observed. Einstein argued that they had independent reality, prompting his famous claim that God does not play with the universe. After understanding quantum entanglement, it is clear that God does play dice with the universe and sometimes throws them where they cannot be seen. Quantum teleportation. Before getting into quantum teleportation, let me give an idea about teleportation. See, teleportation is the hypothetical transfer of matter or energy from one point to another without traversing the physical space between them. It is a common subject in science, fiction, literature, film, video games, and television. To understand a quantum teleportation, we need to understand quantum entanglement. Quantum entanglement is an uncanny phenomenon observed at the quantum scale or atomic scale, where entangled particles stay connected so that the actions performed on one of the particles affects the other, no matter the distance between two particles, even at a distance of light years. Quantum teleportation is a process in which quantum information can be transmitted from one location to another with the help of classical communication and previously shared quantum entanglement between the sending and receiving location. Quantum information means the exact state of an atom or photon. Quantum teleportation depends on classical communication, which can proceed no faster than speed of light. It cannot be used for faster than light transport or communication of classical bits. While it has proven possible to teleport one or more qubits of information between two entangled quanta. But this has not yet been achieved between anything larger than molecules. Quantum teleportation is not a form of transportation but of communication. It provides a way of transferring a qubit from one location to another. Quantum teleportation was coined by physicist Charles Bennett. Quantum teleportation was first realized in single photons, later being demonstrated in various material systems such as atoms, ions, electrons, and superconducting circuits. The latest reported record distance for quantum teleportation is 1400 km by the group of Jian V. Pan using Messier satellite for space-based quantum teleportation. Next, we will discuss on quantum teleportation protocol. The prerequisites for quantum teleportation are a qubit that is to be teleported, a conventional communication channel capable of transmitting two classical bits, and means of generating an entangled EPR pair of qubits. Transporting each of these two different locations, A and B, performing a Bell measurement on one of the EPR pair qubits, and manipulating the quantum state of the other pair. An EPR pair means Einstein-Fedosky-Rosen pair is a pair of qubits or quantum bits that are in Bell state together. The Bell states, a concept in quantum information science, are specific quantum states of two qubits that represent the simplest examples of quantum entanglement. The Bell states are a form of entangled and normalized basis vectors. We will discuss about the experimental results. Work in 1998 verified the initial predictions, and the distance of teleportation was increased in August 2004 to 600 meters using optical fiber. Subsequently, the record distance for quantum teleportation has been gradually increased to 16 kilometers, then to 97 kilometers, and is now 143 kilometer set in open air experiment in the Canary Islands, done between the two astronomical observatories of the Institute Autofisia de Canarias. There has been a recent record set as of September 2015 using superconducting nanowire detectors that reach the distance of 102 km over optical fiber. For material systems, the record distance is 21 meters. Researchers have also successfully used quantum teleportation, quantum superposition. See, quantum mechanics is a fundamental theory in physics that describes the physical properties of nature at small scales of the order of atoms and subatomic particles. It's the foundation of all quantum physics, including quantum chemistry, quantum field theory, quantum technology, and quantum information science. Quantum superposition. See, quantum superposition is a fundamental principle of quantum mechanics. It states that, much like waves in classical physics, any two or more quantum states can be added together or superposed, and the result will be another valid quantum state, and conversely, that every quantum state can be represented as a sum of two or more other distinct states. Superposition refers to the quantum phenomenon where a quantum system can exist in multiple states or places at the exact same time. In other words, something can be here, there, up, down at the same time. Mathematically, quantum superposition refers to a property of solutions to the Schrodinger's wave equation. Since the Schrodinger equation is linear, any linear combination of solution will also be a solution. An example of a physically observable manifestation of the wave nature of quantum systems is the interference peaks from an electron beam in a double-slit experiment. The pattern is very similar to the one obtained by diffraction of classical waves. The double-slit experiment discovered that electrons and all quantum particles both exist as particles and probability waves. Quantum particles exist as probability waves means that we don't know for certain where these particles are. We can only know the probability of where they will be. In other words, particles can be here, there, up, down at the same time. In quantum realm, it's really magic. It's an illusion. Example is a quantum logical cubic state as used in quantum information processing, which is a quantum superposition of the basic states 0 and 1. As you know, the basis of quantum computing is the qubit, unlike normal computer bit, which can be 0 or 1. A qubit can be either of those, a superposition of both 0 and 1. That's what it's shown in the figure. In the classical computing, you have 0 and 1. But in qubit, it's a superposition of both 0 and 1. I will discuss about the superposition and the Schrodinger's thought experiment. See, Schrodinger's cat is a thought experiment, sometimes described as a paradox, devised by, Austrian physicist Erwin Schrödinger in 1935 during the course of discussion with Albert Einstein. In Schrödinger's imaginary experiment, You place a cat in a box with a tiny bit of radioactive substance. When the radioactive substance decays, it triggers a Geiger counter, which causes a poison or explosion to be released that kills the cat. The cat ends up both dead and alive at the same time. Because the existence of a cat that is both dead and alive at the same time is absurd and does not happen in the real world. This thought experiment shows that wave function collapses are not just driven by conscious observation. Quantum superposition versus superposition of classical waves. You need to understand quantum superposition is fundamentally different from superposition of classical waves. A quantum computer consisting of n qubits can exist in a superposition of 2 raised to n states. In contrast, playing n musical sounds with all different frequencies can only give a superposition of n frequencies. Adding classical waves, wave scales linear, where the superposition of quantum states is exponential. That's why most of the optimization problems and we use quantum computers to solve most of the optimization problems and problems that grow exponentially. So that's all about quantum superposition. Quantum tunneling, it's an interesting concept. To illustrate quantum tunneling, consider a ball rolling along the surface with a kinetic energy of 100 joule. Let's assume as the ball rolls, it encounters a hill. To get clarity, you can see this figure. See, as the ball moves, it encounters a hill. The energy needed for the ball to climb the hill is 1000 joule. The ball proceeds only part of the way up the hill, stops and returns in the direction it came based on the laws of classical physics. But you need to understand, we do not expect even after repeated attempts for the 100 joule ball to ever be found beyond the hill. Therefore, the probability that the ball passes over the hill is exactly 0, and probability it is turned back or reflected back by the hill is exactly 1. The ball never makes it over the hill. The existence of the ball beyond the hill is an impossibility or energetically forbidden. So now, what is this quantum tunneling? That's what I am going to discuss now. This is possible. See, we understood that in classical physics, it's not possible for the ball to climb the hill with 100 joules of energy. But this is possible in quantum level or atomic scale. Quantum tunneling is the quantum mechanical phenomenon where a wave function can propagate through a potential barrier. Quantum tunneling is a phenomenon in which particles penetrate a potential energy barrier with a height greater than the total energy of the particles. So you understood what quantum tunneling was first noticed in 1927 by Frederick Hunt, a German physicist. Max Born, who was instrumental in the development of quantum mechanics recognized the generality of tunneling. See, here I have shown the tunneling in diode. I will explain that. See, Max Born realized that it was not restricted to nuclear physics, but was a general result of quantum mechanics that applies to many different systems. The study of semiconductors and the development of transistors and diodes led to the acceptance of electron tunneling in solids by 1957. It's shown in the figure. This is electron tunneling in diodes. In 2016, quantum tunneling of water was discovered. In the year 2016, water molecules breaks bonds through quantum tunneling. Now we are going to discuss about the interpretation, why this quantum tunneling occurs. The reason for this difference between classical physics and quantum mechanics comes from the treatment of matter in quantum mechanics as having properties of waves and particles. One interpretation of this duality involves the Heisenberg's uncertainty principle, which defines a limit on how precisely the position and the momentum of a particle can be known at the same time. So you are familiar with this equation, delta x into delta p greater than or equal to h by 2, where h is the Planck's constant, is 6.632 into 10 raised to minus 34 joule seconds. Delta x is the uncertainty in position and delta p is the uncertainty in momentum. See, this implies that the uncertainty principle implies that there are no solutions with a probability of exactly 0 or 1, though a solution may approach infinity if, for example, the calculation for its position was taken as a probability of 1, the other, that is the speed or momentum, would have to be infinity. Hence, the probability of a given particle's existence on the opposite side of an intervening barrier is non-zero, and such particles will appear on the other side with a relative frequency proportional to its probability. That's what Heisenberg's uncertainty principle says. In physics, two wave sources are perfectly coherent if their frequency and waveform are identical and their phase difference is constant. Laser light is an example of coherent source of light. Quantum coherence deals with the idea that all objects have wave-like properties. If an object's wave-like nature is split in two, the two waves may coherently interfere with each other in such a way as to form a single state, that is, a superposition of the two states. Quantum coherence and quantum entanglement are two landmark features of quantum physics, and now physicists have demonstrated that the two phenomena are operationally equivalent, that is, equivalent for all practical purposes, though still conceptually distinct. This finding allows physicists to apply decades of research on entanglement to the more fundamental but less well-researched concept of coherence, offering the possibility of advancing wide range of quantum technologies. Although physicists have known that coherence and entanglement are close relatives, the exact relationship between the two resources has not been clear. It's well known that quantum coherence and quantum entanglement are both rooted in the superposition principle, the phenomenon in which a single quantum state simultaneously consists of multiple states but in different ways. Quantum coherence deals with the idea that all objects have wave-like properties. If an object's wave-like nature is split into two, then the two waves may coherently interfere with each other in such a way that as to form a single state, that is, a superposition of the two states. This concept of superposition is famously represented by Schrodinger's cat, which is both dead and alive at the same time, which in its coherent state inside a closed box. Coherence also lies at the heart of quantum computing, in which a qubit is in a superposition of the 0 and 1 states, resulting in a speed up over various classical algorithms. When such a state experiences decoherence, however, all of its quantumness is typically lost and the advantage vanishes. The second phenomenon, quantum entanglement, also involves superposition, but in this case, the state in a superposition are the shared states of the two entangled particles rather than those of the split waves in a single particle. The intrigue of entanglement lies in the fact that two entangled particles are so intimately correlated that a measurement of one particle instantly affects the other particle, even when separated by a large distance. Like coherence, quantum entanglement also plays an essential role in quantum technologies such as quantum teleportation, quantum cryptography, and super dense coding.